Here is a beast of a math problem filled with nested square roots. It looks intimidating, but our goal is to tame it, one step at a time. Let's dive in. The most direct strategy to solve an equation with square roots is to eliminate them. And the way to eliminate a square root is by squaring it. We'll start with our original equation. Squaring the left side will cancel the main square root. On the right, we'll evaluate 2 squared. This looks much simpler already. We've eliminated one radical, but 2 remain. And here is our result. The radical is now isolated. But wait. Before we rush forward, this equation gives us a vital clue about our solution. Let's look at this equation again. This gives us our first constraint. 4 minus x must be non-negative, which means x must be less than or equal to 4. We also know from the original problem that x must be non-negative, so any valid solution must be between 0 and 4. Let's store this clue and continue. Now, back to our main path. Here's where we left off. The square root on the left is gone. Now we need to expand the right side. This gives us 4 minus x times 4 minus x. Multiplying the terms gives 16 minus 4x minus another 4x plus x squared. Combining the middle terms, we get 16 minus 8x plus x squared. We subtract x from both sides and combine the terms to get this elegant quadratic on the right. This quadratic expression x squared minus 9x plus 16 must be greater than or equal to 0. Let's call this constraint 2. Now, let's combine all the information we have gathered before moving on. Our first constraint told us x must be between 0 and 4. Our second constraint says this quadratic must be non-negative. To see what this means, we need to find its roots. Using the quadratic formula, the roots are at approximately 2.44 and 6.56. Since the parabola opens upwards, it's non-negative outside of its roots. So x must be less than or equal to 2.44, or greater than or equal to 6.56. This leaves us with the final, combined constraint. Our solution must be between 0 and approximately 2.44. This is an incredibly powerful deduction. We've reached a complex equation. Squaring it again leads to a monstrous quartic in x. A more elegant path is to simplify it with a substitution. Here is our equation. Notice the relationship between the terms involving x. With y equals the square root of x, it follows that x equals y squared. Now we substitute y and y squared into our equation. Simplifying the powers gives us this. And rearranging gives us a new quartic equation, this time in the variable y. So how do we solve this? A general formula for quartic equations exists, but it's a monster. We don't need it. We can use logic. We can't easily find the exact answer by hand, but we can prove a root exists in our allowed range using a beautiful idea from calculus, the intermediate value theorem. Let's define our quartic polynomial as p of y. We know our solution for y must be between 0 and about 1.56. Let's test points in that range. Let's start with an easy point, y equals 1. Evaluating the powers gives 1 minus 9 minus 1 plus 16. The result is 7, which is a positive number. Now let's test a point near the other end of our constraint, y equals 1.5. 1.5 squared is 2.25, and to the fourth power is 5.0625. 9 times 225 is 20.25. Combining the positive and negative terms separately, we get a negative number. Since the function is continuous and changed sign, the intermediate value theorem guarantees that a root must exist somewhere between 1 and 1.5. Now that we've logically proven a root exists and pinned down its location, we can confidently use a numerical solver to find it. The value is approximately 1.465. Now we substitute back to find x. Since x equals y squared, we square our value for y. We arrive at our one true solution. X is approximately 2.146. This value satisfies every constraint we discovered along the way. Let's substitute our solution for x back into the original equation and verify that it works. Evaluating numerically, we see that the left side is approximately 2, confirming our solution is correct. If you enjoyed this solution, please subscribe for more math adventures.